Alright, today we're looking at the projection of vectors 20D. We're gonna look at using the previous part with the scalar product, and it is a concept that you already use implicitly. With Cartesian coordinates and a Cartesian plane, you have your horizontal axis and your vertical axis. They do already have any vectors that you have in that environment where are already separated into two components, the horizontal one and the vertical one. The horizontal is with the I vector and the vertical with the J vector. It is actually a projection of vectors that you already performed. With this section, you should be able to project any vector with any new equivalent vector similar to I and J in any direction. The application of it will be when we move on later to kinematics, is when you're looking at a modified Cartesian plane where you don't want your reference vector I and J to be horizontal and vertical. And in year 12 you'll see you will deal with situations when you have an inclined plane, so an object that is sliding down a slope. So that would be a further down application. So let's go back to the basic. How do we do a projection of vector? Is first you have your vector A, which is in a sort of random direction, which is equivalent to an angle theta to its component u. Let me mention first is to do a projection, what you do is you need to generate or draw a right angle triangle. So you have your vector A here, and you have a vector B here, which is horizontal. You will have to manipulate your drawing to make the vector you want to project onto to be horizontal, just for it makes it easier to read it. And what you do is you draw your vertical line, which is perpendicular, and you can see now you have your right angle triangle. That's your adjacent, that is your opposite if you relate to your trigonometric ratio. And that vector, which is on your adjacent with that length and the same direction as B, is perpendicular to W, and A is the sum of those two vectors that are perpendicular. Okay, so let's look at the geometric representation using formulas. So from that diagram, vector A is equal to vector U plus W. You can see that U is parallel to B, so we can express U as a scalar amount times B, and W is perpendicular, but what it is because it's a sum. So here you have a sum. If we make W the subject, it's a difference of A minus U, and it's vector A minus KB. So keep that in mind for the opposite vector, because this is what we're going to be using later on to find the second vector. Now we want to find first the vector U, which is the projection in the direction of B. And here, yeah, hang on, oh yes, this is the proofing. So for W to be, we want W to be perpendicular to B. We do W dot product B, we rearrange it. What we come down to, so have a look at the detail working out, which is the proofing to determine the expression of U. I'm just going to skip those steps and move on to the important part. You have your coefficient K, but what it is the vector U can be re-expressed as, in terms of vector B. Remember, scalar products are scalar, so that's a quotient, that is a scalar amount, and that new expression for the vector U is called the vector projection projection or vector resolute of A, that vector A, in the direction of B. Just be really careful when you read an exam or SAC question that the order of the vectors in which you decide the direction is critical. If it was the other way around, it will change completely the expression. So if it was in the direction of A, it means that U will be a vector in the parallel to A. So just be careful with the wording of the question. Alright, so moving on with this. So the general rule, hang on, so this is done, we've done this already, that's fine. Sorry, it's a repeat of the slides. Wait, let me pause that so I get through the examples. Let's continue with the vector resolute or projection. So here you have that notation, so that's what we've seen in the previous slide. Here it's a little bit going to be rearranged to regroup the vector B over its magnitude. What it is when you have your vector B and you divide by its own magnitude, you end up with a unit vector. It's the same direction, but it's all magnitude of all that vector multiplied by the reciprocal of that magnitude. That will end up with a magnitude of 1, and that's the notation for a unit vector. So this is an alternate notation that you could use. I would still advise to use the first one, as it is the expression you would use to evaluate the scalar amount here, and B is the given vector usually from the original question. Do you remember that vector A is the sum of U and W? So W will be the difference, and we can just do the substitution, do the difference, and you need to rearrange it to just to make it more appropriate. Also, with this expression of U, that is the unit vector. This is a scalar amount, and that scalar amount is also called the scalar resolute of A in the direction of B. So if it's the question is asking you for a vector resolute, you need to express it as a vector, and if it's asking you for a scalar resolute, it's a scalar amount. Okay. To summarize that, you have U, vector U, we have an expression of vector W. If you do the sum of the two, we get an expression of vector A in terms of two components. One component is parallel to B, and the second component, which is W, will be perpendicular to B. And those are the rectangular component, one parallel to B and the other perpendicular to B. Okay, so it's just all about the language. Probably a good idea to go back to the right angle triangle drawing, have that in your bound reference, and annotate the new terms. First example, you have two vectors. You need to find the vector resolute of A in the direction of B, and vice. This is going to be the opposite. Now you need to find the vector B in the direction of A. So make sure you apply the correct formula. It's going to be in the direction of B, so you have that is your expression of the vector resolute. So A dot B over B dot B times vector B, and that gives you your vector. Just verify this vector has to be parallel to B. If I multiply that by -1, it's equal to B, so it's actually in the same direction. Well, it's in the opposite direction, but it's parallel. B in the direction of A, so now we need to express as a vector A the denominator is the a dot a. The scalar product is commutative, so it's going to be the same as the part A. You evaluate that, and that gives you your expression. As you factorize the negative 1/5, you can see that's your vector A, so it is parallel to A. So it's really linked to 20C when you use the dot or scalar product. Another example, so you need to find again it's an application, find the scalar resolute. Because it's scalar, it's just the coefficient that we need to find, not the vector. It's going to be parallel to B because that's the question mentioned, it's in the direction of B. So what you do the dot product, you do your magnitude. This time it's not a magnitude square, it's just the magnitude because we need to find just that amount. You evaluate that. Don't forget to rationalize your surds. Also, don't forget, if you had to simplify your surds as well, in this square root of 10, 10 is made of factors 2 and 5, so there's no hidden perfect squares, but just be mindful to simplify your answer. If you do that on your CAS calculator would simplify it for you. Okay. I think that would be the last one. So this one, you need to resolve. You have your vector I plus 3j, which is your vector A. It's asking you for rectangular components, one of which needs to be parallel to that vector, and that's your vector B. Okay. So because it is asking you for your rectangular components, you need to find your vector U and W as well, which is the sum for that will be equivalent to vector A, which is this one. So annotate, label the vectors, find your vector resolute of A in the direction of B. You use this formula. It is critical you get that correct, so always double check that you get that correctly. Which is, let's say you get your answer here. It needs to be correct because you're going to use this expression to determine the perpendicular resolute that will generate a secondary error if that one was incorrect. So you have your vector U here. You can do the difference now from vector A minus U. You simplify and regroup the coordinates, and now we can express our vector A in terms of two parts. That's our vector U, that's a vector W. If you have time, double check that they are perpendicular. So if you do the dot product, and the dot product is pretty quick, you just multiply the x and the y's. Be mindful of the correct signs, and that needs to be equal 0. So if it equals 0, you have indeed find two vectors that are perpendicular, so that makes it a rectangular component duo. Okay, and that's it for 20D. So I'll see you later.